Alan, the term Big Bang is in popular parlance. Everybody sort of knows it and talks about it. But there's imprecision in what that really means. What does it mean?
Yeah, well, that's right, there is. And I think it's not really a scientific term, so it's defined by popular parlance, which is kind of vague. To some people, the word Big Bang means the instant of creation. In the scientific circles, when one talks about the Big Bang theory, that actually is a well-defined concept. And it really, surprisingly, in spite of the name Big Bang, really says nothing about the Big Bang itself. It says nothing about what banged, why it banged, or what happened before it banged, I like to say.
Or how you got all the material in the bang.
Or how you got all the material in the bang, exactly. So the Big Bang theory is really the theory of the aftermath of a bang. And it's a theory that describes the expansion of the early universe, assuming that it started in a very hot, dense state. It assumes that all the particles are already present and that they have already been set into motion. And the theory then describes how the universe expands, cools, describes how the early chemical elements formed, how eventually the stars formed. There's a lot in the theory, but it does not describe the bang itself. A twist called inflation that I've worked on attempts to describe the bang of the Big Bang, the thing that caused the universe to propel into this gigantic expansion that we still see the aftermath of today.
So what is inflation? How does it work? And I might slightly correct you in that you created it in addition to working on it.
Thank you. Inflation is based on ideas coming out of particle physics, which tell us that our theories predict that at very high energies, and this does involve extrapolating our theories beyond where we tested them, so it depends on the extrapolation, but the theory predicts that at very high energies, there should actually exist forms of matter which turn gravity on its head and cause gravity to behave repulsively instead of attractively. And the inflationary theory is basically the hypothesis that this repulsive gravity was the bang of the Big Bang. It's what set the universe into this period of gigantic expansion.
And you were able to have a doubling of the size of the universe in a very rapid time.
That's right. The gravitational repulsion leads to an exponential expansion, which means that there's a certain time in which the universe doubles, and if you wait the same length of time, it doubles again and then doubles again.
How much time do you have to wait? Not too much.
Not too much. To get the universe from the size that we think it had at the beginning of inflation to what it needs to have had at the end of inflation, to ultimately include everything that we see, requires about 100 doublings. And 100 is not a huge number. These doublings happen unbelievably quickly. There's some flexibility in the theory about exactly when in the history and at what speed inflation happened, but a very plausible answer to those questions would be that inflation happened using the physics of what particle physicists call grand unified theories. And if that's true, then the doubling time was about 10 to the minus 37 seconds, decimal point, 36 zeros,
Wow.
one at the very end. Unbelievably short length of time.
So if you have 100 of these, it takes 10 to the minus 35.
That's absolutely right. 100 of them, and it's 10 to the minus 35 seconds.
So in this
Still
period
an
of time,
unbelievably short length of
the
time.
whole universe as we know it was created.
Essentially, that's right. Inflation is not a theory of the ultimate creation of the universe, in that to start inflation, one needs a little bit of matter, approximately a gram, it turns out. But inflation does not describe the ultimate beginning. But once you have this gram, inflation actually does describe how all the rest of the matter that we see, which of course is vastly more than a gram, is created during the inflationary
And that's
process.
absolutely incredible, whether it's 10 to the 80th or 90th amounts of protons and the same number of all different other kinds of particles, photons. All of that is created from this 1 gram using inflation during this incredibly short period of time.
That's absolutely
Now,
right.
it sounds like we're getting something for nothing, because how can you have energy being created when we know there's a very tight law of conservation of energy and matter?
Correct. It does sound amazing, and I sometimes refer to the inflationary creation of the universe as the ultimate free lunch. But it is all consistent with the laws of physics as we know them, including this, as you say, very tight principle that we believe is exact, that total energy is always conserved. The shocking thing is that even though total energy is always conserved, one has an instinct to believe that energies are always positive, so that to have a lot of energy in some place, you need to have started out with a lot of energy someplace. That's what falls by the wayside. Inflation takes advantage of the fact, which has really been part of physics for a long time, that not all energies are positive. And in particular, the gravitational field has a negative contribution to the total energy of whatever system it's part of.
So all the particles that are created have create a gravitational field, in effect, and bends curved space and all that. So that negative energy of the gravity they produce balances out the positive energy of the fact that they're coming into being in the first place.
Exactly. So as inflation goes on, more and more positive energy goes into the creation of matter of various kinds, but at the same time, more and more negative energy is created in the form of this gravitational field that just fills the ever-expanding region of space, and they balance. So the total energy remains what it was when we started, which was very, very close to zero. And shockingly, it really is consistent when we look at it in our observed universe, that the total energy in stars and galaxies and vast amounts of matter that we see throughout the observed universe is canceled by the negative contribution of the gravitational field that fills the universe.
Yeah.
So the total energy of our universe is consistent with being zero.
Now, all of this matter then is created at the end of inflation.
That's right. It's created in the form of this repulsive gravity material as inflation goes on,
And
but becomes normal matter at the end of inflation.
Okay. Now, in this incredible process, which is exciting, but it sounds fantastic in every sense of the term, including unbelievable. Now, the reason this has become such a powerful theory is that there were some problems prior to inflation with the standard Big Bang theory that inflation dealt with in a very fascinating way. So how did that work?
One example is what's sometimes called the homogeneity and isotropy problem. Homogeneity meaning why is the universe the same at all locations, isotropy meaning why the universe looks the same when you look at all directions. Those are actually independent if you think about it carefully. The universe appears to be both, as far as we can tell. The most precise evidence for the isotropy of the universe, which is what we know the best, comes from observations of the cosmic microwave background radiation, which we view as the afterglow of the heat of the Big Bang. Astronomers have made very sensitive measurements of this radiation, and what they find is that after you account for the motion of the Earth through the radiation, which causes an anisotropy, if you track that out, the residual anisotropy of the radiation itself is at a level of about 1 part in 100,000. To a level of 1 part in 100,000, it's the same intensity, same effective temperature,
so it's very
no matter which way
homogeneous.
you look.
Yeah.
So it's apparently incredibly homogeneous. Technically, this is isotropy.
Right.
It could be inhomogeneous if there were shells that surrounded us. Then it could be inhomogeneous and still isotropic. It's highly implausible. Nobody thinks that. But that's the distinction between the two words. So how does one explain this? In the conventional Big Bang theory that existed before inflation was invented, the universe expanded so fast that there was no way that the universe could have come to a uniform temperature before this radiation was released, before the radiation that we're seeing came into being. One could have always assumed that the universe started out completely uniform, but that's just an assumption, not an explanation. Inflation provides a real explanation, because in inflation one inserts into the history of the universe this period of extremely rapid exponential expansion. And the implication of that is that the region that's going to ultimately become the piece of the universe that we see before inflation started was unbelievably small. In fact, it was more than 1 billion times smaller than the size of a proton, if the numbers that we're estimating are right. While it was so small, there was plenty of time for it to become uniform by the usual mundane processes by which temperature becomes uniform. Take a slice of hot pizza out of the oven and put it on the table, it gets cool. Those processes. For very small things, it happens very fast.
Okay, so that's...
Then, once this uniformity is established on a very small scale, inflation takes over and stretches it to become large enough to encompass everything that we see, while at the same time maintaining this uniformity of temperature.
Okay, problem one solved. Problem two.
Problem two is referred to as the flatness problem, and it's flatness in the terms of the geometry of the universe. And I should maybe clarify, I'm not talking about a two-dimensional universe. I don't mean that by the word flat. By the word flat, what I really mean is non-Euclidean. According to general relativity, a general universe does not have to be Euclidean. The space could be what's either called open, closed, or right on the borderline of that is the Euclidean case of flat. And also, according to general relativity, this geometry is linked to the mass density of the universe. For a given expansion rate, you can calculate using general relativity a number called the critical density. And if the actual density is more than that critical density, then the universe is closed. Less than the critical density, the universe is open. Only right at this one special number, the critical density, is the universe flat, Euclidean, like the geometry that we all learned in high school. We know today that the universe is very close to this critical density. One refers to the ratio of the actual mass density to the critical density as omega. So cosmologists are always talking about omega. Omega equals 1 means the universe is flat. Omega greater than 1 is closed. Omega less than 1 is open. Today we know omega is equal to 1 to within a few percent, which already seems surprising. But the really surprising thing, the so-called problem that inflation solves, this flatness problem, is not the value of omega today, is what you find when you extrapolate it backwards to the very early universe. It turns out that omega having the value of 1 is an unstable point. If it's exactly 1, it remains 1 forever. But if omega in the early universe were just a tiny bit more than 1, it would rapidly rise towards infinity. And if it were just a little bit less than 1, it would rapidly fall off to 0.
In the first case, the universe would instantly collapse into a giant black hole, or in the second case, it would expand so fast there'd be no galaxies and no stars possible.
Exactly correct.
And we know that both cases are not the case.
Both cases are not the case. That's right. Both of those cases are not the case. So omega has to have started out extraordinarily close to the number 1. And the number that I like to quote is really the number I first learned from Bob Dickey way back when, before inflation was invented, which is that if you extrapolate backwards to 1 second after the Big Bang, omega must have been equal to 1 to an accuracy of 14 decimal places. A decimal point, 13 zeros, something like that. Incredibly small value. Now, in the conventional Big Bang theory, there is nothing that fixes the initial value of omega to be 1. Omega could have been 1, but it could have been 2, or 10 to the 5, 10 to the minus 5. Any number is equally logical. It just has to be extraordinarily close to the number 1 to get a universe that looks like the one we live in. So it seems to be an arbitrary choice.
How does inflation solve it?
Inflation solves it by changing the way the universe evolves during this period of exponential expansion. Even though it's incredibly short, it's incredibly important in terms of the effects that it has on the universe. During the period of inflation, when gravity is turned on its head, instead of omega equals 1 being unstable, it becomes extraordinarily stable. And no matter where you start, you're driven towards omega equals 1. I think the easiest way to understand this intuitively is to remember the link between omega and geometry. It's easier to understand this from the point of view of the geometry. What inflation is really doing is it's taking an initial space which might have been curved. Picture a sphere as an example. If you take a sphere and rapidly expand it, then if you look at any fixed size piece of it, it looks flatter and flatter the bigger it gets.
Like the surface of the Earth.
Exactly, like the surface of the Earth. It looks flat to us, even though we know that it's really round. Same thing with space-time. If inflation is right, the space on a very large scale might very well be curved, but it's been expanded by such a vast amount that the piece of it that we see inevitably looks flat. And that's the solution to this flatness problem, which is one of the 2 key problems of classical cosmology that inflation provides a solution to. Going on in terms of consequences of inflation, there's one rather important prediction that inflation made, which seems to work surprisingly well. I mentioned that the cosmic microwave background radiation is uniform to 1 part in 100,000. But it's not completely uniform. We actually do see non-uniformities at this level of 1 part in 100,000. And the amazing thing is that astronomers have really managed to measure these non-uniformities now to very extraordinary accuracy. Inflation makes a real prediction for the spectrum of these non-uniformities. And by spectrum, I mean how the intensity of the non-uniformities, think of them as ripples, how the intensity of these ripples varies with the wavelength of the ripples. According to inflation, the origin of these non-uniformities comes from a rather bizarre mechanism. It's quantum theory at work. It's simply the idea that underlying all of physics is a probabilistic description of reality called quantum theory. And that means that even if the classical version of inflation would just say that everything is stretched and becomes uniform, when one puts in the quantum theory behind that, the uniformity that would have been predicted at the classical level suggests that it's almost uniform, but because of the quantum uncertainties, in some places the mass density and initial temperature would be a little bit higher than average, in other places it would be a little lower than average. And those are exactly the kind of ripples that one sees in the early universe through this cosmic background radiation. And the spectrum that's predicted from these assumptions turns out to match beautifully with what has been observed. It's a spectacular success, and one that I was just amazed that they can measure it at all. In fact, they've measured it now very accurately, still continuing to measure it more accurately as the years go on. And so far, all of the measurements have been consistent with the basic predictions of inflationary models.